Welcome to another exercise in the statistics workbook. This time I'm going to focus on multiple linear regression. What is the task here? Well, the revenues of an ice cream vendor in 1,000 euros are collected for 5 random days, together with the day's average temperature and its active ads from the preceding week. We get the following table. And here we already marked the revenues with y, so describing they are the dependent variable, and the temperatures with x1, the ads with x2, marking them as independent variables. And, well, this table summarizes the data for the 5 days. Our tasks now: first, calculate the linear regression equation that describes the relation between the 3 variables. Second, calculate the coefficient of determination, the r-squared. And finally, conduct a suitable test to check for a margin of error of 5% whether the determined model has significant explanatory power. Let's more or less conduct an f-test. Well, let's start with the first part. First part, calculating the regression coefficients. And here we have a multiple linear regression. So we're using the following formula, whereas x is the matrix concerning or containing all the values for the independent variables, and y is the vector containing all the values for the dependent variable. So here we have those two: dependent variable, independent variable 1, independent variable 2, and we have this column here with ones describing the intercept. So in the result, we will get this vector b containing the intercept first, then the coefficient for the first independent, and then finally the coefficient for the second independent variable. So in the next slide, we're going to insert this vector and this matrix into the formula. We're going to do this. We get this partial result. This first matrix, to make it a bit simpler, already is x transpose times x and thereof the inverse, because here we're focusing on the statistics and not so much on the math part. So this is first part. Then we have here matrix x transposed, and we have the vector y. So in the next step, I'm going to multiply these two matrices, giving me this result. And then finally multiplying this matrix with this vector, giving me a vector with just 3 entries. And as I said, the first entry, that's the intercept. That's the coefficient for my first independent variable. That's the coefficient for my second independent variable. So that my regression line finally will look like this: intercept plus 0.2028 times first independent variable plus 1.3497 times second independent variable. This regression line we're going to use in the next step when we're going to calculate the r-squared. So here we're going to focus on the coefficient of determination, the r-squared, and we can use the following general formula for this, showing us that we actually need 3 additional values for this. The average of y, that's easy to do. We already have all the values for y. Then we need the average of y squared. And that's also pretty easy to come by. Just square all y values and take the average. This part up here, that we actually have to do some work. So I'm going to copy the table we had from the exercise. That's actually this part up here. And I'm going to add 2 rows. In the first row, the last row, I'm adding the y squared. So simply taking the y values to the power of 2. And here in this row, I'm going to calculate these y hat square values. What is y hat? Y hat is the value I get if I insert x1 and x2 in my regression line, the one I calculated on the slide before, and calculate an estimate for the original y. That's the y hat. This estimate I'm going to square, giving me these results. These values actually should be pretty close to the y squared I have below this. They will be much closer the better my regression line actually is. So here I see, well, they look decently well, especially if I now add one more column where I calculate the mean of y squared, and the mean of y hat squared. And see those two, that's actually the important part, those two are pretty close to each other. Well, I take these three values, I insert them in a formula for r squared, giving me an end result of 0.9878. So in other words, my regression line can explain 98.78% of the whole variance of the dependent variable. And that's actually pretty good. But well, still the question remains, is this good enough? Meaning we have to conduct an F-test to actually check whether our model has explanatory power, significant explanatory power. That's what we're going to do on the next slide. So we conduct an F-test. For the F-test, first off, we need the test statistic. This is the following formula. So we need the r squared. That's what we actually calculated in the slide before. We need k. K is the number of independent variables. Here we had two x variables, x1, x2. So two independent ones, k being 2. And we need n, the number of observations. Here we had 5 observations, so n being 5. Then we insert these values in the formula, r squared, 1 minus r squared, k being 2, n being 5, and we calculate a value of 80.9672. That's the test statistic. To actually conduct the test, we also need a reference statistic. So we're going to turn to our tabled values for the F statistic, and we're going to look up the value f k n minus k minus 1, 1 minus alpha. K, we noted was 2, n was 5, so n minus 2 minus 1 is 2 as well. And the alpha is the margin of error, which in our exercise text was named as 5%. So we should use alpha 5%. So in the last part we get 1 minus 5%, so 0.95. This value we're going to look up in the table. And there we're going to find a reference value of 19. So we're going to compare the test statistic, the 80 point something, so 81 more or less, with the 19. That's the test decision. And we see, well, the 81 is much larger than the 19. So we can reject our H0 hypothesis. The hypothesis which holds is the H1. And the H1 hypothesis states that the model has significant explanatory power. So we actually have a pretty good model. And well, that's then everything there is to this exercise. So I hope you enjoyed it. I hope you learned something. I'll say goodbye. See you next time.